Soon we're going to discuss all the changes that were observed in the last 20, 30 to 100 years. All the changes induced by humans, induced by the greenhouse effect, due to the emissions of CO2 and other greenhouse gases. We will talk about all these observed changes, but these observations were only possible because of the rapid advances in the monitoring of weather and climate conditions and the modeling, the development of climate models. Okay, so this lecture talks about the advances made in the climate modeling and monitoring space. All right, and this lecture has two parts. In part A, we talk about observing systems. We're looking at the land-based stations first. Okay? Then we look at methods to map vegetation. Then I talk about satellite technology, just a brief overview. Okay? And then talking about marine observing systems. And there's a range of significant advances made, like the development of Argo floats. Yeah. The second part focuses on climate models, and climate models are the key to predicting future changes in the climate. Okay, so what's a climate model? How does it work? So I try to explain this to you. I give you an overview. We talk about the history of climate modeling and what to expect from a climate model prediction. And what is model validation, or how do you validate a model? And what's ensemble modeling? Okay. So let's get started. Let's talk about observing systems first. Okay. And we start with land-based observing stations. Okay. So the first thing are automated weather stations. Okay, they're at fixed locations, usually at airports. Okay, fixed locations and measuring a range of key atmospheric parameters, like wind velocity, temperature, air pressure, relative humidity, solar radiation, cloud cover, precipitation, usually at a reference level of 10 meters above ground. Okay? And that's one part of information that is used in weather forecasts, to provide initial conditions for weather forecasts. Okay? All right. So, that's the automated weather stations. And then in larger cities, we have air quality measurements undertaken regularly. It's based on human health, and we measure carbon monoxide, nitrous dioxide, ozone, sulfur dioxide, total suspended particles. Okay, it's related to human health. Okay, like asthma. And related to bad air quality, illnesses. We have flux stations, and flux stations measure the exchanges of carbon dioxide, water vapor, and energy between the biosphere and atmosphere. We have radiation measurement, plus soil data. Soil measurements are often available too. And here it's all about the fluxes at the surface. In addition to that, we have gas monitoring towers that measure CO2 concentrations at greater heights. Can be several hundred meters heights. And there are the key ones measure CO2 and methane concentrations. Okay, that's monitoring the concentrations. And they play indeed a very important role in the context of global warming. In terms of atmospheric measurements, we also need information on the vertical structure in the atmosphere. And that's why we use so-called weather balloons, balloon-based weather observations that are released at the surface, and the balloon rises through the air column, taking with it a radiosonde which has a number of sensors, and it measures vertical profiles of pressure, temperature, and relative humidity. And we need that for the weather prediction as well. Because weather prediction is based on a computer-based model, but you always need to start with precise as possible with initial conditions so that you can predict into the future. You always need to correct the computer model. And that's why you need these vertical profiles too. In addition, we use radar for precipitation measurements over land. We can derive the horizontal distribution on relatively small scales. It's also used for weather prediction. And let's just briefly talk about the aerial mapping. It's about the mapping of vegetation, if you like. Or the mapping for the development of cities. So, common methods used, modern method is based on drone-based video surveys. But traditionally we use a method called LiDAR, which is light detection and ranging, which is a method of mapping that allows high levels of detail to be recorded about topography and vegetation and related features. And here are some maps. You can see the high resolution that you get from the light detection and ranging mapping. All right, so this is land-based stuff, and we need to know more for the climate system. We need to know about the oceans, surface conditions over the oceans. It's 70% of the world's surface. That's why satellites are so important. Let's have a look at satellites, just very briefly, not going too much into the details, but what type of information we get. From satellites, we get information on cloud cover. We get information on vegetation, which is based on a normalized difference vegetation index, and you can look that up. We measure solar exposure, rainfall, surface wind fields over the ocean, outgoing long-wave radiation, ocean color, chlorophyll A, which is the green pigment in phytoplankton, sea surface temperature, which indeed is a key parameter, the temperature, and sea ice extent and drift, indeed very important in the context of global warming. We measure also the sea level height. So satellites can actually detect changes in sea level. Although they're only in the range of millimeters or so, satellites can detect these changes. Surface roughness and wave height. We can change, you could detect wave height. And that's it. And satellites play an immensely important role. For weather forecasting, but indeed also in the context of climate change. Because now we have data since the 80s, which is 40 years of, a little bit more than 40 years of satellite data. And that's a very good piece of information. It should be highlighted that satellite data only capture the surface information of the oceans. In some instances integrated, say, over the top 10 meters or so, if you look at ocean color, the chlorophyll A content, but not below. So we don't, with satellites we can't detect changes in the ocean interior. So we still have to use marine vessels, and methods, sea-based methods. Alrighty. So let's talk about marine observing systems, and the first one is also connected to land. It's a land-based method. It's something we call a tide station or a tide gauge station. Okay, and it's a station that records the average sea level. Not the waves, not that, just the average sea level, okay, and how it changes from 1 hour to the next. So it's related to the tides, and you have a high tide and a low tide on time scales of 12 hours or 24 hours and of that order. Okay. And so it's a method, and it's shown here in this map. It's a method which actually where there's an inlet at the bottom, and where you don't get that information of waves near the surface, and you just that one is just filled through the pressure effect and just records the average sea level goes up or down. It's often connected with other sensors like temperature sensors and so, and and it's sent to satellites, and that's how you get the data for these stations nowadays. All right. Oh, there's an image here above my head. It shows the very old San Francisco tide station run by NOAA, which is in operation for more than 150 years. You have that tide station here. So how do we traditionally measure ocean parameters? So what we do traditionally comes not on this slide, comes on the next slide. So let's just look for completeness at a list of or map of all the tide gauges that we have, so that you get a feel for it. Okay. It's very, very similar to weather stations. So you have a very high number of tide stations in northwestern Europe, around the North Sea. As you can see here, all these little dots are tide stations. And on the west coast of North America, there are the most stations. Also on the east coast here, also on the west coast. And other stations, we don't have that many tide gauges. Yeah. But now let's talk about the other method. And this is called CTD. It's a CTD method. So you're on a ship, and what you do is you have a very long wire, and you lower an instrument into the water, which is actually, you can't see here, it actually sits in the middle, okay, which is called a CTD. And what it does, it records data to calculate salinity and measures the temperature and measures the depth through pressure data on the ocean. And all the bottles that you can see around here are so-called Niskin bottles, and they can be closed at selected depth to collect a water sample. So you can collect water samples, say at 3,000 meters, 4,000 meters. You have a number. This one is one. Probably have something like more than 30 bottles. And then you can use the water for chemical analysis. You can determine the nutrient content and so on. Okay. So that's the old method, and we're using methods like that CTD from the 1960s or so. Before that was only water sampling. Yeah. Very labor-intensive method, and imagine how big the oceans are. Based on these methods, you don't have that many stations, and not everywhere in the oceans. What you also can do is you can collect time series of marine data through so-called moorings. Moorings are deployed sensors, and it shows you two examples here. One which they have a weight at the bottom, and then buoyancy keeps them upright. In this example, with a subsurface float. And there are a number of instruments hanging in here, and they can measure temperature, salinity, currents, and water quality. There's some can measure dissolved oxygen. Depends on the sensors that you put in here. Okay? And often we have an acoustic release system at the bottom. We can come and with a specific code, and then it releases, and that will float back to the surface, so you don't lose your instruments. And there are instruments that have a surface, floating surface device, which contain atmospheric sensors. You know, you can have a weather station at sea. Okay. All right. Again, you get information on specific locations. You know, you can have instruments at different depths, but you can have recordings over 2 years, or sometimes even longer, and you learn quite a bit of local changes. Alrighty, so now the revolution in oceanography came with the development of Argo floats. Okay? So Argo floats are autonomous instruments that sink and measure in the ocean to target depth. Okay? Shown here on this map, sink to 1,000 meters, then drift for a number of days, 10 days in this example, and then even descend further. Some even go down to 6,000 meters. But most of them actually only go down nowadays to 2,000 meters. Okay, and then they go back. You know, it's done through changes of the buoyancy of that object, and then they send all the data to satellites, data transmission to satellites, and then they continue. Okay, and you get these vertical profiles, and the key parameters measured are temperature and salinity in particular. But there are also examples of Argo floats which have biochemical sensors on them. Okay? All right. And here above my head, showing you a map of, and this one is for February 2018, one example of the locations of Argo floats in the world ocean. Okay, so this would not be possible with ships, you know, having this coverage. Okay, and they can be in the water for a year or two, you know, and then they are maintained and exchanged and stuff. You know, you don't lose these floats. Okay, they will be collected after some time. And in this, the color coding here shows you which countries are involved, and you can see it's a global initiatives, you know, with the number of floats per country. And Australia is a big player in that, in particular for the Southern Ocean. And that is really a big a revolution in oceanography, because we didn't have that detail of observations before. Okay. And this concludes the first part of this lecture.